Good morning or afternoon or evening, everybody, depending on where in the world you're joining us from. For me, it's 7 a.m. Sort of local time. And welcome to this keynote presentation for our advanced analytics session. I'd like to thank the University of Adelaide who are kindly sponsoring this session. My name's David Preen. I'm the Chair in Public Health at the University of Western Australia. And I'll be chairing this session. I'd like to start by acknowledging the traditional owners of the lands that we're all meeting on today. For me, that's the Whadjuk Noongar people in Perth, Western Australia, and I'd like to pay respects to elders past, present and emerging, as well as any Indigenous people who are joining us for the session today. So just very quickly, as you probably will have seen, we have Louisa Jorm, who will be giving a keynote for about 20 minutes, and then we'll have around about 10 minutes for questions. As per the usual process for this virtual conference, if you could please post your questions using the live Q&A function, which will be on the right-hand side of your screen. I'll monitor those as we go, and then we'll facilitate the questions towards the end. If there are particular questions that you see other people post that you really would like to prioritize or you sort of would like to ask, you can like those particular questions, and then I'll be able to get a guide as to sort of what the audience are hoping to hear in terms of the questions, given we have fairly limited time. All right, well, it's my pleasure now to introduce our keynote speaker, Professor Louisa Jorm, who I've had the pleasure of working with in the linked data space for many years. Louisa will be well known to many of you, I'm sure. She was the Foundation Director of the Centre for Big Data Research in Health at the University of New South Wales. She's also worked in senior leadership roles in both government and academia. And is an international leader in health big data research, specifically applying advanced analytic methods to large-scale, routinely collected data. So it really is a perfect person for our keynote to kick off our advanced analytics session. She's played a number of leading roles in establishing major linked data research infrastructure and capacity, and that includes a major and primary involvement with the development of the New South Wales Centre for Health Record Linkage, and also more recently the development of the e-research institutional cloud architecture, or ERICA secured data analysis. She's certainly a high-profile advocate for better use of routinely collected data for improvement in policy and practice in the health space. So without any further ado, I'd like to hand over to Louisa.
Thank you, David. And thank you very much, conference organisers, for inviting me. And I'd also just like to echo David's acknowledgement of the traditional owners of the land on which we're all meeting. In my case, it's the Gadigal people of the Eora Nation in Sydney, and it's 10 a.m. in Sydney. And a few minutes ago, someone started mowing the nature strip outside, but it seems to have passed. So, but apologies if some noise enters into the background here, because I'm actually at home here. I'll just start to share my screen now. Hopefully you can see that now. Thinking about this talk, I actually sort of changed the title slightly because I'm wanting to focus on, I guess, some things that I have learned over the last probably 3 or 4 years while working at the Centre for Big Data Research in Health and observing the sort of intersection between the world of machine learning, AI, and that of the more traditional epidemiology, which is where I came from. And I think there is a real imperative right now to try to bring these worlds together. And I guess that's going to be the focus of what I talk about today. Just before going any further, just disclosure slide, which I think is increasingly important in this AI-enabled world where there are many, many commercial interests out there. I don't have any relevant financial relationships with commercial interests. This is now quite an old slide. It dates back to 2012, but you've probably all seen it, this idea that the data scientist is the sexiest job of the 21st century. I definitely am a data scientist as well as an epidemiologist. But if you try to find a good definition of data scientist, it's not easy to find. But what I've got up here in the top corner is, I guess, a fairly, I think multiple people will give this as a definition of a data scientist. It's someone who actually does have domain-specific expertise, but combines that with analytic skills to extract knowledge from data to drive action. And looking at that definition, surely epidemiologists are perfectly placed to be the data scientists in health, healthcare, and medicine. But are they? And looking around at what are considered to be the core skills for healthcare data scientists and what are sought when people are trying to employ healthcare data scientists, top of the list, machine learning and use of the open source programming languages R and Python. And in fact, for people who've been working in epidemiology for years, other non-open source, closed source languages such as SAS and Stata have been pervasive, and it's really only in more recent years that R and Python have started to emerge. Also really important, apparently, for a healthcare data scientist is being really good at storytelling, which is, I guess, making complex analytic concepts and analytic results understandable to a healthcare audience. Interestingly enough, though, that only about 1/5 of epidemiology programs offered by the top public health schools in the US actually do have a course in data science as mandatory. So I think we are somewhat behind the 8 ball in trying to incorporate the skills that, in fact, the workplace is looking for in data-enabled healthcare professionals. So I've come up with what I think are some priorities for what I'll call machine learning enabled epidemiology. And that's what I'll focus on today, just giving a few examples of these. I think it's really important that anyone working in our field has some understanding of the foundational concepts of machine learning and types of machine learning models, familiarity with machine learning terminology, which is actually quite often different for the same concepts. Eventually, we'll all have to start coding in R and Python and leave SAS behind. And I think there's currently a major underuse of some of the data science tools for reproducible research, such as GitHub and Jupyter Notebook, and a reluctance to share code, and there's still not a culture of sharing code for us. And then I think there's many opportunities that we're not really capitalising on to use machine learning to enhance classical, what you might call classical epidemiology, enhancing outcome and exposure measurement, enhancing causal estimation, opening up for our analyses new data sources that are too large and too complex for traditional methods. And then also we have a lot to offer to the machine learning world in terms of developing approaches that incorporate epidemiological thinking. And so robust consideration of confounding causality and bias, for example. So I'll just work through each of these priorities. Firstly, in terms of foundational concepts of machine learning, many of you, this will just be teaching to suck eggs, but I thought I'd go through some of the major classes of machine learning. And I think many people, when they talk about it, are thinking about what's called supervised learning, which is where you basically have input data that is already labelled with an answer, with a gold standard. And the learning algorithm basically tries to map from this input with the labels and then generalize to new data. So, in this example, we've got a training data set that contains labeled imaging results for cancer or not cancer. The algorithm learns from this labeled data set such that when a new example comes in, it hopefully predicts the correct label for that example. And these are just some of the types of machine learning models, supervised machine learning models that are used. You'll be interested to see that logistic regression is listed there, a tool of the epidemiologist, but it's also a tool of the machine learner. Basically, it's a form of predictive modelling, and all of these supervised learning techniques are really predictive models. Just an example from some of our work. using supervised machine learning, where basically we were trying to look at a range of deep learning architectures for predicting readmission to the ICU. So we had a labeled data set where we knew who was and wasn't readmitted to the ICU. And then we could look at a very large number of predictors in what was this case, an intensive care unit electronic medical record data set. And these are just some of the, the findings, very traditional looking findings, because we layered a logistic regression layer as a final layer in a deep learning model. And so you end up with what for us is very familiar odds ratios with their 95% confidence intervals for a range of different predictors of readmission. Perhaps a bit less known to many people from epidemiology backgrounds is the idea of unsupervised learning, where basically the input data does not have target labels and the data themselves are just used to model structure, distribution within. So, clustering and dimensionality reduction would be common types of unsupervised machine learning. And you probably have seen examples of for example, of k-means clustering or principal components analysis. Again, something we know of from statistics, but it is a form of dimensionality reduction or clustering unsupervised learning model. An example of some work we've done, which is basically unsupervised learning, was using a large sample of Australian Medicare data, Medicare claims data, to identify patterns of patient sharing amongst general practitioners and gain an understanding of the sort of structure of general practice in Australia. So these, for example, are clusters of general practitioners who share patients amongst each other. So you've got very large clusters with multiple GPs sharing many, many patients. And then you've got rather more distributed clusters with fewer GPs and very limited patient sharing. We could then go on to look at the characteristics of the care that is provided by these different structures of general practice interaction. Again, perhaps even less familiar is reinforcement learning. And I think this is the form of machine learning that probably comes closest to what people think of as being starting to approach artificial intelligence, where a machine learning algorithm, which in this case is called an agent, basically takes action, gets feedback or reward as it's called, and then it tries to maximize its positive rewards. So it learns basically from almost experimentation or action and then getting feedback. And so, for example, if we're looking at something like a physiological parameter, maybe blood glucose, the machine learning algorithm may decide to activate an autonomous insulin pump. But then it will get feedback. If it's had an unfortunate outcome, it will know that that was possibly not the best action. It will learn from, from that experience. And then in future, when presented with a new, a new case, it will hopefully take the right action based on that sort of reinforcement learning loop that it's gone through. And examples of reinforcement learning are listed here: cue learning, actor-critic learning, and state action, reward, state action. This is probably, even though reinforcement learning has been around for a long time, there's been very little utilisation of it in healthcare, even though it has obviously a lot of potential for healthcare, because so much of what we're doing is a continuous longitudinal process of taking actions. One of the big issues is that we just don't have data that are readily shareable at really detailed patient level about the time series of actions and events and healthcare activities and their outcomes that can be basically shared in ways that preserve patient privacy. Yes, this is an example. As I said, there's only a few examples of development of reinforcement learning in health. And here's an example where they developed a thing which they're calling the Artificial Intelligence Clinician, which learns optimal treatment strategies for sepsis in intensive care. So an interesting paper to have a look at, where they actually have put this into practice and demonstrated quite good performance of this AI clinician. Then there's deep learning, which is, you probably hear about all the time, and has really, in many ways, just revolutionized the whole world of machine learning, and for both supervised and unsupervised and reinforcement learning, there are deep learning approaches to all of those. I guess my somewhat simplistic description of what deep learning is that it's based on artificial neural networks, but it uses a cascade of multiple processing layers to progressively extract higher level features. And many of the very successful applications of deep learning are in the image analysis area. So all of the facial recognition type of work that's going on currently, it all uses deep learning. It basically breaks down an image into pixel and then goes through a series of these hidden layers where it identifies higher level features to eventually come up with a prediction that this particular image was, for example, a dog. Much of the deep learning is supervised, but there are also unsupervised deep learning approaches. And all of these are forms of supervised deep learning: recurrent neural networks, convolutional neural networks, and generative adversarial networks, which are ones where you pit two neural networks against one another. And some very interesting sorts of results coming out in the healthcare domain of use of these generative adversarial networks for tasks like creating synthetic data that preserves privacy. And just back to this is the paper I sort of presented earlier showing where we developed deep learning architectures for predicting ICU admission. I guess the thing that we could do that a normal logistic regression would have just fallen over was we had a very, very large number of ICD-9 diagnoses as well as medications and other treatments in the data set, and we're able to generate parameter estimates for those in terms of how much importance the neural network placed on them when making its prediction decisions. And this is a thing called attention. Because the neural network is all based on this idea of thinking, the model is said to give attention to things in the way that it makes its prediction. And these were the diagnoses that got the most attention, i.e. were most important for predicting that patient was going to be readmitted. And when you look at them, they sort of make sense as things that would be associated with fairly serious complications. So in terms of familiarity with machine learning terminology, as I mentioned earlier, many of the terms that we use in epidemiology or biostatistics have slightly different names for the same term in machine learning. So predictors or covariates, independent variables get called inputs or features. Outcomes or dependent variables get called outputs, targets or labels. Regression is used in epidemiology or biostatistics, both for continuous and categorical outcomes, but in machine learning, regression relates to continuous outcomes, while they call categorical outcomes a classification problem. So fitting is sort of similar to training or learning. Dummy variables are sort of similar to the wonderful term one-hot encoding. Positive predictive value is exactly the same as precision in machine learning, and sensitivity is exactly the same as recall. So you'll see this just different terminology being used, and it's important that we understand that it's actually things that are quite familiar to us, just with a different name. Coding in R and Python. Just sort of a brief comparison of SAS, Python and R. SAS has been around for a long time, since 1976. It's one of the most expensive pieces of software out there, particularly if you're in a non-academic sort of environment. But it does provide a sort of end-to-end solution in terms of a full data warehousing and a lot of data management capabilities, which many people, in my team, for example, still find SAS the best tool for data management. But increasingly for machine learning tasks, Python and R reign supreme. Both of these are open source and free. Python is a very general programming language that can be used for multiple purposes, while R has really grown out of the statistical community and the academic community, and the academic community develops R packages and makes those available. Clearly, they don't have the same type of necessarily testing behind them as something like a new procedure in SAS. And so it's a much more dynamic environment in terms of new packages coming out all the time, but also they can fall over and they may still be in beta at the time that you take them on board. people in my team are using both Python and R, and in our health data science courses, we actually teach SAS, Python and R, because I think it's important that you're not a monolingual data scientist. I'm not going to get into this argument, but the R versus Python communities are quite sort of active. I think really many recognise that both of them have particular strengths, and increasingly R is increasing its machine learning capabilities, while traditionally Python has been supreme in that field. So, sharing of code and use of data science tools. Again, I think we have a lot to learn from machine learning communities, computer science communities in this regard. Code sharing is basically the culture in machine learning and basically in engineering, and making your code freely available and shared through mechanisms such as GitHub is the norm there. It really has not been the norm for us, and I actually think it is a problem for the reproducibility of so much of the work that we need to code. I have actually in the past done a survey of my staff about code sharing, and the reason that some are reluctant to share is not that they don't want to share their IP, but they feel embarrassed about their code. So it does come back to this idea that we do need to build stronger coding skills and a different culture of perhaps being a little bit less precious and worried about our code and more willing to share something that may not be totally perfect, with the idea that there will be reuse of that and feedback on that. An example of this sort of sharing idea, this is a piece of work that we did where we calculated travel times by road from every statistical area in Australia to every hospital in Australia, and then made that available as a data descriptor paper. And I think it's already got a few citations, even though it was only published fairly recently. So now that there is this potential to publish data descriptor papers, that is a way of sort of getting recognition and citations for this sharing type of work. So moving on to how we use machine learning to enhance classical epi. I've got a couple of examples here. This is a recently published paper from International Journal of Epidemiology, Tony Blakely et al., which looks at how machine learning can assist in improving causal inference. And they propose that there are big advantages in applying machine learning for predictive tasks where the coefficients themselves do not need to be interpreted, but you're actually just trying to produce the very, very best prediction that you can. And so examples of such tasks are calculation of propensity scores, calculation of inverse probability of treatment weights, G computation and targeted maximum likelihood estimation. So in all of those cases, the best prediction is what you're trying to achieve, rather than worrying so much about the interpretation of the individual coefficients. And I apologise, the lawnmowers reappeared in the background. Not much I can do about it, I'll speak up. Another area where I think machine learning is starting to enhance epidemiology is opening up new data sources that were just previously inaccessible to us. And electronic medical records are a key example of that. So you'll all be aware these are records that are basically person-centered, collected through commercial software in either general practice settings or hospital settings, but typically contain very multimodal data. So they may contain images, they may contain laboratory test results, they may contain physiological monitoring information. Typically they contain a lot of free text data. None of those things have been very accessible to us as epidemiologists or able to be used for our modelling, but machine learning can help us here. And just again, an example of work that we're currently doing. One of the big problems with trying to use these electronic medical record data is the fact that free text contains lots of identifiers. It contains doctors' names, patients' names, dates of birth, and de-identifying these is actually totally necessary before you conduct any other research using such data. And we've actually developed, still hasn't still being submitted for publication, this particular piece of work, a model for automated de-identification of hospital discharge summaries that will then open up this data source, which contains incredibly detailed and rich information compared to routine hospital administrative data for our research purposes. And that diagram there just shows the approach for developing what in this case is an ensemble model, which uses multiple different models and takes the best of all of those to produce the best performance for de-identifying these summaries. And then finally, developing machine learning approaches that incorporate epidemiological thinking. And here is where I think machine learning is often criticised as being a black box, and that correlation does not equal causation. And it's all very well to predict something, but if you don't know why it's going, you know, what the predictors are, or what the importance of various predictors are, how can you actually do anything about it? And, you know, how do you stop there being problems with confounding, collinearity, bias, where there's just a black box, a whole lot of variables fed in and then an output fed out with little understanding for a human of what's actually happened in between. And here's where I think epidemiologists really do need to start to work alongside machine learning experts. Very recently published in the BMJ is this paper that actually compared statistical models and machine learning for predicting clinical risks for patients, in this case cardiovascular disease. And what they compared, you can see there a range of different models, ranging from logistic regression models through to random forests, neural networks, you know, some machine learning models of various types. And you can see from that, the plot there, that there's really a quite big variation in the predictions for individual patients that these different models will take. And this particular set of authors found that models that ignored censoring, and that is just assumed censored patients to be event-free, were likely to substantially underestimate the risk of cardiovascular disease compared to a traditional survival model, a Cox model or a parametric survival model. That's not surprising. Clearly, if you leave out people who've been censored and assume they basically didn't develop disease, that is going to introduce bias. It's not a surprising result. But what was a bit surprising is that this group didn't actually try to use any machine learning techniques that incorporated censoring, and they do exist. And so we're sort of pleased to see this paper.
Louisa, sorry to interrupt.
Yep.
Might, if that's all right, we might just cut you off now. Just notice we've got about 8 minutes left for questions.
I'm almost there.
Oh, okay, all right.
Almost there. So just to say that there are machine learning models that can actually bring together survival analysis and deep learning to incorporate censoring, which is and this is a piece of work we're currently working on. So this was my very last slide, and again, it was just a bit of a exhortation to people. It's a bit tongue-in-cheek. You know, this source is the median annual wage of an epidemiologist, obviously US, is $70,000 compared to a data scientist at $120,000 a year. I think it is imperative that we start to move towards being the data scientists in healthcare and medicine. And that is my last slide. Sorry that I was over-enthusiastic.
Great, it's good to be enthusiastic, and well done with fighting the background noise. It sounds like you have quite a palatial backyard from this.
It's actually the front nature strip.
Oh, there you go. All right.
So I have no control. It's the council out there mowing it. I've got no control.
So you can write your strongly worded letter later. So we've just got a few minutes left, and we do have a number of questions. So first one is from Michael Scholl, and he's asked, what is your experience with machine learning researchers' desire to import or export code into secure analytic environments and balancing this with privacy and security concerns?
The main issue that we have is not really around importing or exporting code. It's more that there are just very few data sets that are available. And you probably saw that one of the pieces of research that I presented used the MIMIC3 data set, which comes from Boston, and a huge proportion of the machine learning in healthcare scientific literature uses that data set. because it is one that has sort of been made HIPAA compliant and released relatively openly. It has various, you know, obfuscation of dates and obviously no identifiers in it. But there are very, very few other data sets that are available. And machine learners typically all want to use the same data set and benchmark their models against one another. If you can't access the data, it's really hard to do that.
Great. So another question here, which I think you've touched on a little bit, and from James Rafferty. So can you comment on, whoops, sorry, that's just moved. James, can you comment on open source in a little more detail and why people from a more epidemiological background might be more reluctant to embrace this open source culture? I was interested in your comment about that. That's because they don't want other people looking at their code in case effectively they're identifying some issues. But do you have any more thoughts on that in terms of the overall culture? We had a similar comment from Christine Work in that, do you think requiring code sharing as part of one's job and role could build a culture of sharing within and across organisations in this space? So two questions there relating to the open source and the sharing of code and other aspects.
It's just, it hasn't been the traditional culture, and it partly is that we have used these closed source software, Data SAS, I think in your case, Data SPSS, but that's the software side of it. But the unwillingness to share code, I think it's just part of the culture of engineering and computer science that they do that, and it hasn't been part of ours. There is a little, you know, a sense of sort of competitiveness, I guess, amongst health and medical researchers that might be something, you know, one of the reasons that's impeding them. But I think it's been a lack of tools as well, and a lack of training in the tools. So once, you know, our staff started to become aware of GitHub, and a couple of people started to use it and then present seminars and workshops to help others to use it, the fact that it has huge advantages in terms of version control and those sorts of elements, and helps teams to work together. And to use the same code and enhance the same code and gain value more quickly. I think providing them with the tools and some training in the tools and some incentives to use those tools. And again, you can actually publish code papers now. A number of journals are now accepting those. So I think that again does provide that incentive. If your code can actually add to your citation count, that's always going to be an incentive for an academic.
Okay, great. And yes, you're right. Thanks for pointing out I am a dinosaur and traditionally use SPSS, although my analysts and postdoc have dragged me kicking and screaming to Stata and R and some other sort of packages in more recent years, albeit begrudgingly. So a question here from Jacqueline Stevens. What are your thoughts on how we can, and if we should, better implement the FAIR data principles in Australia for epidemiological data, and I guess in particular for machine learning and other.
So fair data principle, definable, accessible, interoperable, and reusable. I totally sort of agree that we should be trying to implement them, but the big problem that we have in the sort of data linkage and administrative data community is that we cannot share those data because they're owned by a data custodian agency. So I think it's trying to establish the FAIR principles as something that public data custodians should be trying to uphold as part of being a custodian or a steward for those data, is what we need to do. I mean, many of us will have run into issues with journals where you have to provide a statement about data availability. And all we can do is say, well, we can tell you how to access the data and who you need to contact, but we cannot share just because of the nature of the fact that we're reusing data that are owned by government agencies. So I think in Australia, there's a new Data Accessibility and Transparency Act that is being developed. And you know, underpinning that is this idea that public data should be accessible for public good. Hopefully that act may help to change some of the data custodian attitudes and behaviours.
Great. So I just noticed we have a minute and a half left. So maybe the last question that looks like it's sort of come through in the list. So is from Anonymous, but not that controversial. So you gave us many applications of using machine learning AI in the healthcare context. One of them was hospital ICU readmission. and they were interested in what solutions are currently being used in real-world hospital readmission context.
This is a very good question, because you will find a large number of papers in the literature that are trying to predict readmission, and relatively few implementations. And one of the problems is it's actually very difficult to implement new sort of workflows within the electronic medical record environments. And also there's still a lot of research needs to be done about interaction between clinicians and these sort of AI tools. And are they acceptable to clinicians? How can they be, how is their usability going to be tested? How do you evaluate them? Do you need to do RCTs? Is it appropriate for an Australian hospital to buy a black box AI solution that's been developed using data in Boston? And you know, that all of this is swirling around, but it's an area where there's very little real world application at this point. And I think we need the implementation scientists on board, as well as the machine learners and epidemiologists.
Great, thank you, Louisa. So we do have some questions pouring in, but I notice we have 50 seconds left, and thank you for the to tech support for extending this session by a couple of minutes, but I think we should probably wrap that up there. Thank you for a fantastic presentation. A lot of the comments and the questions or comments that have come in have just said thank you. It's been very helpful and really insightful. Certainly very interesting, and something that we're all going to be dealing with sort of going forward. I'd like to thank you again, Louisa, and also thank the University of Adelaide for sponsoring this session. And thank you to those who posted questions and have dialed in. So we might leave it there, and I hope you enjoy the rest of the advanced analytic session coming up after a 10-minute break.